Hello, Math 13 students. Let's talk about section 5.2, the binomial distribution. I'll review some very basic definitions. We'll go over the requirements, and then we'll talk about how your calculator makes the binomial distribution calculations. You will need your calculator for this material. There really is no good way to do it without your calculator. If you take a look at the PowerPoint presentation for the 5.2 material, there is a formula, but honestly, once the formula is used once or twice, we move on and have our calculator make all the calculations. I will note that some students may have access to something called the Binomial 83 program. If that is the case, reach out to me and I can help you make that work. Or you can just use the keystrokes you see here. Everyone has the tools on their TI-84 that I'm going to use here today. It's really a very powerful machine, and we're going to see some of that power today. Let me go ahead and share my screen. And let's see. There we go. All right, so section 5.2, binomial distributions. We have some worked examples. We're going to look at two distinctly different tools, one for calculating a single p of x, the other for calculating what we call a sum of many. You can see their names there. The naming convention is a little bit shortened up, but basically you have the binomial probability distribution function and the binomial cumulative distribution function. Two distinctly different tools for two distinctly different problems. Let me move my camera up here, and let's go ahead and go. Outline. In this presentation, we're going to review the basics of a binomial distribution, and I'll hit the definitions. Then we're going to use your calculator to calculate a single p of x and then a sum of many. We have a number of examples to make this happen. I'll start with the definition of a random variable. It has a single numeric value determined by chance for each outcome of a given procedure. If that seems confusing, think about the number of boys and 10 burrs, or the number of times you're going to see snake eyes if you roll the dice, pair of dice 30 times, whatever the case might be. The probability distribution is a graph or a table or a formula that gives the probability for each value of that random variable. So you have the value of the random variable and the probability that that value appears in the processing of this procedure. Here in chapter 5, we look at what we call discrete random variables. These outcomes can take on only a finite number of values or possibly countable, which is a mathematical term, not to be worried about here. Usually it's going to be the number of successes. So the kind of things that we look at literally are the numbers like 0, 1, 2, 3, 4, 5. Not 1.5 or 3.9, number of successes. Either you succeed or you don't. So, discrete. Now, the actual definition of a binomial distribution has to satisfy these 4 requirements. If what you're looking at does not satisfy these 4 requirements, I'm sure it is very interesting, but it is not a binomial distribution. Probably something else. Now, a binomial distribution must have a fixed number of trials. No more, no less. You need to decide how many times you're going to roll the dice before you ever pick up the dice. The trials must be independent. The outcome of one trial should have no effect on probabilities of subsequent trials. This is hard for students to identify. This really goes back to chapter 4. I'll say a little bit more about it later. The outcome must be classifiable in 2 ways, only 2 ways. If what you're looking at has 3 or 4 different possibilities, it's really not a binomial distribution, it's something else. Finally, the probability should not change from trial to trial. This is fairly difficult for students to check also, but if you consider things like flipping a coin over and over again, rolling the same dice over and over again, the probabilities would not change from flip or roll to flip or roll. Now, a single p of x, that's where we're going to start. This is going to address the binomial probability question. What is the probability of exactly x successes in n trials? Exactly x, that's the vocabulary I look for to point me into the direction of the single p of x. That's what I look for, that's what tells me what tool I will be using. So I'll use the binomial probability distribution function. I'll show you where that is on your calculator in just a moment. You have to feed it what it needs to eat. It will need to know the number of trials. It will need to know the probability of success in any one trial. That's the P. And it will need to know the number of successes that we are interested in, anything up to and including n. So here's our first example. Well, a recent survey shows that about 11.5% of US residents have never left their home state. We're going to randomly select 8 individuals, and we're going to ask them, did you leave the state? Now, before we get to any probabilities, there's a couple of initial questions that need to be addressed. Are the requirements for a binomial distribution satisfied? If they're not, I'm not going to be able to use these tools. If they are, tools are going to work wonderful. Then I'm going to list N and P and Q. I'll need N and P to make the calculator work. I'll need Q to calculate the parameters for the distribution, which will happen actually in my next video. I'll remind people that because we have 2 outcomes and only 2 outcomes, if you know P, you also know Q. Q is going to be equal to 1 minus P. And we'll see that in a few moments here. So, are the requirements for a binomial distribution satisfied? Well, there are a fixed number of trials, n equals 8, no more, no less. We decide that before we go out and sample. There are only 2 outcomes in play. Either the respondent has left the state, or they have not left the state. Now, the next 2, P and Q, do not change from trial to trial. That's hard to check. We're going to assume that if I select a person over here, that has really no effect on P and Q over there, which also tells me that my trials are independent. Again, these are kind of hard for you guys to check. I know that, I understand that. The first 2 are easy, the second 2 are hard. Now we're going to list N and P and Q. N equals 8. How many trials we have? We make 8 selections. 11.5% of people have never left their home state. So P is equal to, not 11.5%, 0.115. We'll go ahead and convert that percent to the decimal presentation by moving that decimal place 2 places to the left. This also gives me Q. 1 minus 0.115 is 0.885. I'll use that one in the next presentation. Now, the probability. What is the probability that exactly 2 of those respondents have never left their state? I've asked 8. What's the probability that 2 of those 8 have never left the state? So this is where I'm going to use my binomial probability distribution function. Over here on my calculator. So let's see. I am going to need the distribution key, and that's right here. I have the vars key, but right up above the vars key in blue is the word, well, an abbreviation of the word distribution. So, second, vars, and I get a big long list. We're going to go to this list a lot as we go through the balance of the semester. I'll scroll down to fair ways too. Eventually, I'll see a couple of binomial distributions. Binomial PDF, I'll select that guy there, I'll hit enter. Now, I need to enter in the number of trials, 8. The probability of success in any one trial, 0.115. You do realize I could just as easily type in 0.115, it matters not. I'm interested in exactly 2 successes. Now, depending on the type of calculator you have, you may or may not see this particular screen. Once I do have this screen in front of me and I get to paste, I'll hit enter. And I'm dumped off onto the main screen. Some of you may see this screen to begin with. You may need to enter in the 8, followed by the comma key. The comma key is right there, right up above the 7. 0.115 0.115, hit the comma key again, 2, and then I can close them up with the parenthesis right there. In any case, he's in there. I'll hit enter, and I'll round that result to 3 significant digits. I go to the first non-zero digit, 1, 2, 3. So 0.177. But I go one more to the fourth one here. This is a little bit bigger. I look at the 9. That tells me what to do with the 7. So 0.0178 is the probability that exactly 2 of the respondents have never left the state. 2 out of those 8 that we have selected. So there we go. There's our first probability, single P of X. It's the most straightforward of all of them that we do. Now, the sum of many. This is a slightly different question. This one will address the following question. What is the probability of, at most, X successes in the N trials? Importantly, it's up to and including X. This is what we call a sum of many. And these types of problems announce themselves with the phrases at least, at most, more than, less than. I'm sure there's other ways that math teachers torture students, but those honestly are the 4 basic ones that you will run into. I try to use those almost to the exclusion of anything else. It's how the pros write it, by the way. So in this case, we use the cumulative distribution function. And again, it will need the N, the P, and the X of whatever problem it is you are working on, but because it is cumulative, it gives you something a little different. It gives you the sum of probabilities, 0 up to and including X. Now, the basics of this rule go all the way back to the addition rule in section 4.2, way back over there. However, there is no double count here because in these circumstances, these outcomes are mutually exclusive. You may remember me going on a fair deal about mutual exclusivity, events that cannot happen together. So there is no possibility of any sort of double count as we encountered back in chapter 4, and we get to sum the probabilities directly. So 0 through X, I could find all those probabilities using the previous tool, write down all those decimals, add them all up. That's too much work for me. So we have our calculator do the summation for us, and everyone's happier for it. Now, these examples, though, come in several different forms, and these are truly challenging. So let's take a look at them. What is the probability of less than 4 of those 8 respondents having never left their home state? So, less than 4 of the 8. I am interested in possibly 0 of the 8, 1, 2, or 3 of those 8 individuals having never left the state. So that's my probability. It's a sum of many. I'll use that binomial cumulative distribution function. If I go over here to Mr. Calculator, call it the vars key or the distribution key more accurately, scroll down and down and down and down. There we go. Cumulative distribution. Pull them up. 8 goes in. 0.115 goes in, the value 3 goes in, and we'll paste this in. Now, let me come back over here for just a minute and remind ourselves of what it is we're calculating. We're going to actually calculate 4 distinct different probabilities for 4 distinctly different outcomes and sum them together. Back over here on my calculator, I'll hit enter, and I get a 0.99165. My first non-zero number, there's the third. The fourth being 5 or higher tells me that the 1 must be a 2. Back over here in PowerPoint land, I get a 0.992 for this particular calculation. So the probability that less than 4 of those 8 have traveled out of state, have not traveled out of state, 0.992. Very high probability that you'll see less than 4 people raise their hand saying, yeah, I went out of state. Less than 4. Here's our second example. What is the probability that at least 3 of those 8 have never left the state? Now, in terms of my outcomes, what are we talking about? At least 3. That means 3 or more of the 8 have never left their state. That's a lot of people that have never left their state out of a sample of 8. Maybe 3, maybe 4, maybe 5. Now, here's the problem. My calculator can't do that. Not directly, no. I've got to be a little bit tricky, a little bit smart. This is where I need to really understand the notion of a complementary event. My calculator calculates probability, at least cumulatively, from 0 to a fixed value of x. In this case, I realize if I take it up to 2, between the red stuff and the blue stuff, I got everything in my possible outcomes there. So I've got a set A right there, and I've got the complementary event A bar right there. Between the two of them, they span the entire sample space. So what I'll need to do is to set this up in a particular fashion. To find the probability that we have an outcome between 3 and 8 inclusive, what I need to do is to take the number 1, the probability of surety of something happening in the entire sample space, something's going to happen, and then subtract from it the probability of a 0, 1, or a 2 actually occurring. On my calculator, that's not hard to do. 1 minus there's a couple different ways to scroll through your little list a little faster, but not all that many. So we've got 8 again, 0.115 again. In this case, 0 up through 2. So that's what we're going to paste in. So 1 minus, so we've got a kind of complicated little expression there. And there we go. So first non-zero number is the 5. I don't count him. 1, 2, 3. So the 8 tells me what to do with that final 5. So 0.0546. The probability that at least 3 of the 8, at least 3, that means maybe 3, maybe 4, maybe 5, maybe 6, maybe 7, maybe 8, have not traveled out of state is 0.0546, kind of a small probability. Now we have one more example. One more example. Sum of many. Final example. What is the probability that between 2 and 4 inclusive of those respondents have never left their state? So between 2 and 4, I can go up to 4, but that gets me the 0 and 1 also that I don't need. So I think the way to do this is to handle this very much like we did the previous problem, but I'll just take it up to the 4 for the first probability. Then I'll subtract from that the probability of a 0 or 1 respondents having never left their state. Over on Mr. Calculator here, $8.15, not 2 this time. We're going to change that to a 4. All the way up to the 4, we're going to paste that in. I'm not going to hit enter. I need to subtract, minus, back to the cumulative distribution function. Down, down, down. You descend. Ooh, too far. Go back. There he is. Enter, enter. All the way up to 1. Paste them in. There's a lot going on there. You can't even see the whole thing. I will note that this little Arrow here means there's stuff going on to the left that you don't see. Yes, you can scroll back and forth through that to your heart's content to make sure you've got the right numbers in there. But there's a there's a lot going on there. It's all in there. Blow it on, blow on once for luck. Hit enter. And 1, 2, 3, take a look at the 6. So 0.232. The probability between 2 and 4 of those 8 having not traveled, 0.232. So there you have it. You've seen a review of the basics of the binomial distribution. You've also seen how to use your calculator now to calculate binomial probabilities, single p of x being the most straightforward, the sum of many being the one with the most choices to make. You got to set those guys up correctly. You've also have a number of examples to look at. Hopefully that's going to really help as you work your way through the chapter 5.2 material. You need your calculator. I'm going to stop the sharing. And I'll ask that you go away and come back and with some questions. Let me know how the calculator works. Come and visit me during my office hours. We can go through the keystrokes to your heart's content. And anyway, get through that homework, ask me questions. I'm going to leave it there. Goodbye.